Hi everyone, welcome to another lecture of Astronomy 236. This particular lecture bite is going to be about quantum mechanics, which is the physical theory that we use to describe the microscopic and submicroscopic world. I wanted to start off by first asking the question, what is mechanics in general? The definition from dictionary.com is that mechanics is the branch of physics that deals with the action of forces on bodies and with motion. So an example of that is what happens to this baseball when it's struck by a bat. The bat applies a force to the ball and it affects the ball's motion. And the study of exactly how that works is mechanics. In the 1600s, Isaac Newton wrote down this equation, or a similar equation that's close enough to it, that describes the motion of objects we see in every day. This is one of the most famous equations in all of physics. What Newton said is that the force applied to an object is equal to that object's mass times the acceleration of that object. But really, there's an easier way to think about it, which is to rearrange this equation slightly and say that the acceleration an object feels, how quickly that object changes speed, kind of like these two cars here. You see them accelerating at the beginning of this drag race. The acceleration experienced by an object is equal to the force that's applied to that object, in this case, how much force the motors in those cars are applying to them, divided by the object's mass. So you could imagine that if you replaced those cars with trucks, but you kept the amount of force the same, you kept the engine the same, they would not accelerate as quickly as they do, because the greater mass means that the acceleration has to be smaller. And if you kept those same cars and you put a bigger engine in them that had more force, then maybe your mass will increase a little bit, but your force will increase more, and they'll accelerate even faster. I also want to talk briefly about energy. Now, people have a pretty good understanding of what energy is. We think about energy in terms of electricity and in terms of stuff that comes from the sun and from the wind. In physics, energy is a measurement of the ability of something to do work. It's not a material substance. It's not something that I can go and measure. It's something that I have to calculate. Energy can be stored and measured in many forms. And when the Khan Academy here says measured, they mean it not in a direct way. They mean it in an indirect way, which is why I said that you have to calculate it. You can calculate the amount of energy you have from something that is measured. So a few different ways that you might store energy is potential energy. So if you have an object and you raise it up high in gravity, then you have exerted energy to move that object upwards, and you've taken that energy and changed it into gravitational potential energy. It now has the potential to fall downwards and release that energy. There's also kinetic energy, which is the energy of an object in motion. So for example, the kinetic energy from the baseball bat is transferred to the ball, and the ball starts moving faster. And finally, there's chemical energy. There are other types of energy as well, but chemical energy is one of the ones that we see most often in our daily lives. In particular, the energy from the bonds of chemicals in the wood are being converted into light energy in that fire. And the most important thing about energy is that it's not created or destroyed, it just changes form. So in particular with those logs, the logs may be destroyed, but the energy that was in them was not. It was just released in a different way, in particular by heating up the air around the fire and by producing light. So classical mechanics matches our experience and intuition. We have lived in a classical mechanical world our entire lives. And as a result, our brains kind of know how things should behave. That's why when we watch sports and we see players behaving like this, we suspect that the acceleration that they're experiencing does not necessarily match the force that was applied to them. So in these cases, the players are exaggerating the amount of force that was applied to them by the other team in the hopes that that will get the referees to call a foul and help them in their match. But when we look at it on camera, and especially when we look at it in slow motion so we can see just what happened, we can know that there is no way that the amount of force that is, for example, exerted when those two people hit each other's heads was enough to knock both of them backwards like that. So classical mechanics is something that we're all intuitively familiar with. And classical mechanics is extremely accurate. We used the equations of classical mechanics to fly to the moon. It didn't require any of the quantum mechanics that you're about to see. But it completely breaks down when we apply classical mechanics to the submicroscopic world. Instead, we have to use quantum mechanics. Now, quantum mechanics replaces the simple equation F equals ma with a much more daunting one. This is called the Schrodinger equation, and it's listed down here. There's a lot of fancy symbols, most of which may be unfamiliar to you, and there's a lot of stuff going on in this equation. But it kind of has a similar form to F equals ma if you look pretty closely at it. So these symbols psi are describing where a particle might be found at any given time over space. So that's pretty similar to the acceleration term in the force, because if we see an acceleration, then we know where that particle was and where it's now going. We kind of get that same thing here from these psi's that are in the equation. There's a mass in this particle, in this equation as well. That's down here at the bottom under the 2m underneath the h with a bar. And there's also something that maps out the force over all of space, and that's this v term. It's not quite a force, but it shows where forces would be. It's kind of like a map. The Schrodinger equation, unlike Newton's equations, do not describe where particles are. Instead, they describe something called a wave function, which is a way to show where a particle is most likely to be. It's a probabilistic change. So instead of in F equals ma, in classical mechanics, where particles are definitely in places, the Schrodinger equation is a little bit agnostic towards that. So the way you should think of a wave function is kind of like these heat maps that are now being used to describe how things proceed in soccer matches. So you can see here a schematic of a soccer field. And you can see that there's a large area of green, that's kind of the background field. And then there are areas that are colored in yellow and orange and then red. The brighter the color, the redder the color, the more likely a particular player is to have been found there. So if you track a player through an entire match, any given player, this particular player happens to spend most of his or her time in this red region here. So you can imagine that for a defensive player whose job is to stay close to his or her own goal, they will stay on the left-hand side of this field, whereas an offensive player whose job is to try to score goals on the other team will spend more of his or her time on the opposite team side of the field, on the right-hand side here. So wave functions kind of behave in the same way. If you're given a wave function, it tells you where we might find the particle that it describes. So let's imagine that this soccer heat map is really the wave function of some particle. If we were to look for that particle and actually measure where it is, say, for example, by crashing it into a camera, for example, or a detector, sometimes we might see that particle here, but sometimes we might see it here, just kind of bouncing all around this region. But you're very unlikely to see this particle show up outside of these brightly shaded regions in this green region over here. So this would be an unlikely outcome. So in quantum mechanics, we can no longer predict where a particle will go or where it will be with absolute certainty. The only thing that we can predict is how its wave function will change. So the implication of this is that quantum mechanics, and by extension the universe, because quantum mechanics describes our universe, is not deterministic. There is no preconceived fate for the universe, where if we just knew where everything was and where everything was going, we could use the laws of physics to extrapolate forward and figure out what's going to happen. Quantum mechanics says unequivocally that this is not possible. Quantum mechanics is weird. Unlike classical mechanics, which is intuitive and familiar to us, these new laws, this new way of thinking about physics is totally contrary to our experience and intuition. To give kind of an overview of some of the ways this is true, I want you to take a quick break and watch this video that I'm going to insert here from The Fabric of the Cosmos, which is a nice video from the PBS Nova series.
Quantum mechanics rules over every atom and tiny particle in every piece of matter, in stars and planets, in rocks and buildings, and in you and me. We don't notice the strangeness of quantum mechanics in everyday life, but it's always there if you know where to look. You just have to change your perspective and get down to the tiniest of scales, to the level of atoms and the particles inside them. Down at the quantum level, the laws that govern this tiny realm appear completely different from the familiar laws that govern big, everyday objects. And once you catch a glimpse of them, you never look at the world in quite the same way. It's almost impossible to picture how weird things can get down at the smallest of scales. But what if you could visit a place like this, where the quantum laws were obvious, where people and objects behave like tiny atoms and particles? You'd be in for quite a show. Here, objects do things that seem crazy. I mean, in the quantum world, there's a sense in which things don't like to be tied down to just one location, or to follow just one path. It's almost as if things were in more than one place at a time. And what I do here can have an immediate effect somewhere else, even if there's no one there. And here's one of the strangest things of all. If people behave like the particles inside the atom, then most of the time, you wouldn't know exactly where they were. Instead, they could be almost anywhere until you look for them. Hey, I'm gonna have what he's having. So why do we believe these bizarre laws? Well, for over 75 years, we've been using them to make predictions for how atoms and particles should behave. And in experiment after experiment, the quantum laws have always been right.
It's the best theory we have.
There are literally billions of pieces of confirming evidence for quantum mechanics.
There's no disagreement between quantum mechanics and any experiment that's ever been done.
The quantum laws become most obvious when you get down to tiny scales like atoms. But consider this. I'm made of atoms. So are you. So is everything else we see in the world around us. So it must be the case that these weird quantum laws are not just telling us about small things. They're telling us about reality.
All right, now that we've watched this video, we can move on. So there's a couple of implications of quantum mechanics that are going to be important for us going forward. So for the first of these, I want you to go back and look at the Schrödinger equation again. I've now copied it here. And in particular, I want you to look at these curly-looking D things. So in math, these curly-looking Ds are used to denote changes. So in the left-hand side of the equation, we're looking at how the wave function itself, the psi wave function, is changing over time. And on the right-hand side, we're looking at how the wave function is changing in different places. So this is a little bit hard to understand just by looking at this equation. So instead, I want to draw an analogy to another famous equation in physics called the wave equation. The wave equation, as you might imagine, governs waves. Waves in water, it governs waves in string, and it governs waves of light, which we'll learn about in our next lecture. If you compare the way the wave function, the wave equation looks to the way the Schrodinger equation looks, you can see a lot of similarities. Both of them relate changes of a variable of psi in time to changes of psi over space. The implication here is that wave functions and quantum particles behave like waves, hence the name. So what does this really mean for the way particles are and for the way the quantum world works? Well, a property of waves is that if you trap them, so in this case, there's a student here who's vibrating a string, and he's trapping waves inside of the spring by holding one end in his hand and by holding the other end against a hard object, then there are only certain fundamental frequencies that are allowed for this wave to take on. So what do I mean by that? What do I mean by a fundamental frequency? What I really mean is that there is a stationary pattern made by this wave. So you can see that the student is right now vibrating the string up and down, and he is causing the string to kind of make the same pattern over and over again. This is not the only stationary pattern he can make. He can also make one where the string vibrates and moves up and down, but it has two lobes. So you can see on the left-hand side, there's one lobe that moves up and down, kind of like the previous video was doing over the entire string. And on the right-hand side, there's a second lobe, and both of them move up and down. Likewise, he can do this with 3 lobes. He just has to keep moving the string up and down faster and faster as he does this. You can do it with 4, getting harder. And he's even able to get it to work for a very short period of time with 5 of these lobes. So stationary patterns of waves that are trapped have only a certain set number of values that you can take on. If you don't have just that right frequency, if you don't move the string up and down at just the right rate, then you don't get any of these stationary waves. You get something that's a little bit jumbled and looks kind of like this. So the stationary patterns, the standing waves, are special. They're discrete. There's only a handful of them, and they have particularly prescribed values. And they're, in particular, a word we use in quantum mechanics, they are quantized. And this just means that there's only a set number of values that they can take on. Now, I've been talking about waves in strings, and also waves in other media as well. But this basic principle also happens to wave functions that are solutions to the Schrodinger equation. So the implication here is that in many cases, particles that are governed by the Schrodinger equation behave the way standing waves do. And in particular, the energy that a particle can take on are often only discrete quantized values. So particles governed by the Schrodinger equation that are trapped have discrete energy levels that they can have. That's why we call it quantum mechanics.